Good morning, everyone, and welcome to our session on Introduction to Dynamic System Modeling. My name is Nailul Hassan, and I'm excited to guide you through this fascinating topic. Today, we will embark on a journey to understand how we can describe, analyze, and predict the behavior of the systems over time using the powerful language of mathematics. Think of it as learning the grammar of change. Whether it's the motion of robot, fluctuation of the stock market, or even climate patterns, by the end of this course, you will have the skills to turn real-world challenges into mathematical models that guide design, prediction, and decision making. So before we dive into the how, let's first understand exactly what dynamic system modeling is. What is dynamic system modeling? Dynamic system modeling means creating mathematical descriptions of systems whose behavior change over time. Imagine building mathematical digital twin, virtual copy that behaves exactly like the real system. We use differential equations to describe how a system evolves from one state to the next, based on inputs, outputs, and internal states. Why this? Why is this important? Because it allows us to simulate reality, experiment without risk, and gain deep insight before implementation. Whether it's modeling an airplane flight, a robotic arm movement, or even an economic market, dynamic system modeling forms the foundation for smart engineering. Now that we know the definition, let's explore what exactly we mean by a dynamic system. What is a dynamic system? A dynamic system is any system where the present determines the future. For example, a car's current speed will influence whether it will be 1 second from now. The systems respond to time, to inputs, and to internal interactions. Understanding this is crucial because once we know how today affects tomorrow, we can design systems that adapt, respond, and perform exactly as we need. But why go through the effort of modeling these systems? Let's look at the reasons. Why do we model dynamic systems? There are several key reasons. First, to analyze how a system behaves under different conditions. Second, to predict future performance, which is vital for planning and safety. Third, to design systems or controllers that achieve specific objectives like maintaining a stable temperature or balancing a drone in flight. And finally, to stimulate before building anything, saving time, cost, and reducing risk. Without a model, we are just guessing. And in engineering, guessing can be very expensive. To build such models, we need the essential components that make them work. Every model has key components. Inputs component, the signal or actions applied to the system, like pressing accelerator, and we have outputs, the measurable result, like the car speed, internal states, condition inside the system, like temperature, pressure, or stored energy. And most importantly, the mathematical equations that connect them. This framework let us not only describe what's happening, but also predict and control it. Now, there is more than one way to create such model. Let's talk about the approach we can use. Approach to modeling, we can use first principles modeling, which relies on physical laws, Newton laws, for example, conservation of energy, thermodynamics. We can use empirical modeling, which comes from experimental data and statistical fitting. Often, the best models combine both approaches, using theory for accuracy and real-world data for reliability. This blend gives us the best of both worlds. This blend gives us the best of both worlds. Once we have the right approach, we need the right tools. Let's see what you will learn in this course. We will cover powerful tools like Laplace transform, which turns complex time-based problems into something easier to solve. You will work with simulation software to test design before implementation. Most importantly, you will develop a systematic thinking process to break down complex systems into manageable parts. These skills is as important as the equation themselves. And we control the system. We generally work with two major types. Let's explore them. First, open loop systems. These work without feedback. You set a value, but the system doesn't check if it's correct. Example, a basic washing machine. It runs for a set time regardless how dirty the clothes are. Second, closed loop systems. These use feedback from sensor to adjust performance in real time. Example, a thermostat. It constantly measures temperature and adjusts heating or cooling to stay within the set point. In real engineering, closed loop systems are preferred because they are accurate, self-correcting, and adaptive. Now, where do we see dynamic system modeling in action? Almost everywhere. Dynamic system modeling is used in self-driving cars, aerospace, robotics, climate science, medical devices, and much more. If something changes over time, you need to predict or control it. Dynamic system modeling is the way to go. So, with all that in mind, let's end with what you will achieve in this course. By the end of this course, you will able to model real-world systems, mathematically analyze their behavior under various conditions, and apply advanced tools like Laplace transform and simulations. You will also think more systematically, a skill useful in engineering, physics, AI, and beyond. Ultimately, you will have the power to turn complexity into clarity, a skill that will serve you for life. Thank you for attention. I'm looking forward to working with you throughout this course. Let's make the journey ahead both challenging and rewarding.